Okay, our next speaker is Pradeep Ramuhalli. Uh, Pradeep is a distinguished R&D scientist and group lead for the Modern Instrumentation and Controls Group at Oak Ridge National Lab. He also leads a group on measurement and data science applications.
Thank you. I just lead one group, not two, just to correct. So we had a couple of excellent talks in this session, and this is the last talk in this session. And what I'm going to do is just kind of a change of pace. We're going to look at certain capabilities that exist within the national labs that may be useful for testing and evaluation of machine learning. The title here doesn't fully capture the talk, and part of the reason for that is the title was actually put together well before I had all of the details of the talk. But we'll get into a little bit of the perspectives on the testing and evaluation of machine learning solutions from the perspective of assuring reliability, particularly when we talk about safety critical components. The material in this talk is the result of collaborations and work that is ongoing with several people, and they're listed here in the acknowledgements. This is a large group of people at Oak Ridge, but also colleagues at Jefferson Lab and other labs as well. And I'm pretty sure I've missed a few. My apologies to them going through this. Okay. So we'll go through fairly quickly critical infrastructure, emerging needs, and AI, machine learning, and what kinds of solutions are being put together for these emerging needs. And kind of the bottom line message from this entire talk is that assured digital twin technologies are a potential solution for test and evaluation. I think you've heard about digital twins. There have been a few other talks in this workshop on that concept. But my the focus of this talk is on the ability to leverage testbeds and facilities that exist at the national laboratories for developing and building these digital twin technologies. I'll go through a few examples of where we are actually working with existing facilities, existing testbeds, and keep in mind that these are ongoing research activities, which means that we may not be at the end state of, here's the digital twin that you can go and exercise, but we'll get into where we are on every one of these examples. So let's start with some background. Complex systems. I work primarily on the energy side, meaning that I deal with the generation and transmission and use of energy. Every one of these is a complex system, meaning you have complex systems on the generation side. You've got complex systems when you start putting together interconnected generation, transmission. And by complex, I mean that we are really talking about a system that is made up of multiple components, potentially nonlinear effects, emergent behavior. And in every one of these applications, the goal tends to be we want to manage the operation of these complex systems to ensure availability. Energy availability is critical, right? And the need in every one of these applications is for scalable information-driven solutions for managing complex systems and mitigating risk. Whether we want to deal with, wrong button. Whether we want to deal with operations and maintenance decisions of these complex systems for improving reliability, lifecycle analysis, or for design optimization, the fundamental need is for solutions that use models that leverage sensors and data and potentially advanced controls methods. These types of solutions can also be potentially used for training, for workforce development, and diagnostics and prognostics. And several of the examples I'll touch on include diagnostics and prognostics as sort of the end use case. Within this context of complex systems, one of the challenges that we are starting to see within the challenge of complex energy systems, one of the challenges that we are starting to see is a changing mix of generation. If you look at where the energy landscape is today within the United States, if you're going back to about 1950 to about 2 or 3 years ago, the mix of sources that we were using is changing rapidly, with renewables starting to be an increasing part of the mix. Now, what's different about renewables? What's different about wind and solar? These tend to be intermittent, meaning sun doesn't shine all the time, wind doesn't blow all the time, which means that the energy that you get from these is not going to be available all the time. And so we now have a system where we need to start thinking about how are we going to operate this when your source of electricity, for example, is not available all the time, right? But this is today. And today, the focus is primarily on electricity generation. Looking forward, these same systems are expected to be used for multiple other applications. Now, this slide was originally put together to kind of highlight the nuclear energy elements, but the argument still holds, whether you're talking nuclear or any one of these other sources. In energy, electricity is going to be a key output of these systems going forward, but we are increasingly talking about generating hydrogen, clean water, desalination, for example, using process heat for chemical processes or for other industrial applications. And so not only do you have a system where the inputs are going to be starting to change and be different, the outputs are also going to start changing. Managing these systems, controlling these systems is going to be a problem, which means, machine learning, obviously everybody wants to use that. You're going to use machine learning. How do you validate these algorithms? How do you test these algorithms? Particularly when you've got changing contexts, right? This is the key issue. We have data sets going back 10 years, 20 years, 30 years. Those data sets can be used to develop these machine learning algorithms, but those data sets are not reflective of what we expect future conditions to be. How do we test and how do we evaluate these algorithms under those conditions, right? Data sets change. Data collected previously may not reflect current system conditions. And over time, the models that we have developed using these data may drift from the system, and in turn, that's going to affect the ability to interpret the system behavior. It's going to affect the ability to control system behavior. This is for those of you who are into electricity and electrical systems, this is the famous duck curve. Anybody familiar with that? Anybody heard about the duck curve? I think I see a couple of hands. Essentially what this is this was actually put together by the California ISO or CAISO. And what this is the difference between the electrical demand, overall electrical demand, and the demand that is satisfied by renewables, by solar specifically. And what you're seeing here is on the horizontal axis, you've got time from 12 a.m. to midnight, so one whole day, 24 hours. And this is showing how that difference in electrical demand, total demand versus what can be satisfied by solar, changes over the course of a day. Obviously, when the sun is shining, daytime, you can get a lot of solar generation, which means that the conventional sources, whether that is coal, which in California is already gone, natural gas, nuclear, hydro, whatever, they're going to be called upon less. You're not going to need that, okay? But as people start coming home around 5, 6 in the evening, sun goes down, you have increased electrical demand at the same time, and so you now have to make up this difference in a very short period of time. The problem is that conventional electrical sources are not going to be easy to start up and shut down, which means that you got to have them running throughout the day, which means that even though you have the capacity to generate a lot of electricity using solar, you're not going to be able to do that. You'll have to curtail that. So fundamental question is, how do you optimize the operation of these systems when you're dealing with these kinds of curves? And you can see, starting at 2012, this was actually put together in 2013. The expectation was that as you went from 2013 to 2020, there would be an increase, and so you would see a greater dip in that difference, right? Turns out that this dip that is expected here is actually much worse. As of last week, if you look at the data, what you see is not a nice, smooth curve. What you see is a canyon. Essentially, things going flat, drops, 0, back up. Okay? And that is the data from 2023. There is more solar generation that's happening, but the capacity makeup that you have to do at the end of the day is much higher. Okay, so the problem is actually much worse than we expected back in 2013. So my point is, these kinds of conditions exist in real life. We have data from 2013 or 2014. You're not going to be able to build models and then expect them to work under real world conditions today. So what kinds of testing and evaluation tools can we put in place that would allow us to explore these sort of, way off cases, right? And that's kind of where I think the notion of digital twins really plays. What is a digital twin? This is the audience participation section of the talk. So what is a digital twin? Anyone? I know I have an answer there, but anyone? Well, that is one definition. Turns out there was a survey paper that was put out, published about a month ago, 2 months ago. They did a literature review and they came up with 112 different definitions of a digital twin. Okay, I went through that and I know there were at least a few more that they missed. So a digital twin basically can mean anything for anybody, and that's where, to your point of it is a buzzword almost, right? Fundamentally though, the way we are defining a digital twin is it has to be a software model, it has to be a virtual representation, but there are two key characteristics that, if you look at all the definitions, they sort of boil down to these two key characteristics. One characteristic is that it should track the state of a physical system. Okay, if I've got a building and I want to build a digital twin of the building, let's say the building, the HVAC system or the temperature in the room, the software, the digital model should track the physical system. It should track the temperature. Okay, if I build a digital twin of the electrical grid, my software model should track that state of that electrical grid at every second or every whatever, right? So that is one parameter. The other key characteristic is that typically these are designed for a specific purpose. You're going to design these so you can study the system. You're going to design these so you can use this to optimize operations. You're going to design these so you can do something else with it. Now, these two graphics here, these are in some respects what we would call a digital twin. These are actually just software models or representations, but these are included here for a specific reason. Basically, one of the things that is not listed explicitly in these definitions of a digital twin is the fidelity of these models. Okay. On the top here, you have an extremely high fidelity computational fluid dynamics thermohydraulics code for a nuclear power reactor core. And this is showing the temperature, and there's also flow and neutron flux and steaming rate and other key parameters that are computed in this very high fidelity model. This thing takes about 1,000 cores on a high performance computer, couple of days to compute. Okay, but could I use this as a digital twin? Yes, I could, as long as I can make this track a real world system, a real world nuke power reactor core. And that's going to be hard. Here you've got a much lower fidelity representation of an entire plant. Again, the purpose for which this was designed is very different from the purpose for which this was designed. This was designed to optimize design of the core. This was designed to optimize operations. of a plant. And it turns out that this level of fidelity may be okay for the digital twin that we want for this particular purpose. Okay? So a digital twin can be lots of things to lots of people, could be a buzzword, but there are some useful things you can get out of the concept of a digital twin as long as you are aware of the level of fidelity that you need for your intended purpose. I'll skip this. This is the same thing. So within the lab complex, there are a range of facilities. There are bench scale test beds, there are laboratory scale test beds, there are user facilities. Every one of these generates data. Every one of these can be used to generate data, and many of these can be used to run specific targeted experiments. And in many instances, we are beginning to build high fidelity or low fidelity, medium fidelity models representing these different systems. Those systems potentially become available for use as a digital twin for testing and evaluation. And one of the other points I want to highlight is that in many cases, we already have empirically acquired data sets, or we can acquire data sets. But in every one of these cases, we can also augment the data with simulation data sets. So that gives us a larger amount of information that we can use for testing and evaluation. So I'll quickly walk through a few examples here, and let me know if I'm running out of time. I can cut short the examples. But let's start with a very simple example. Arguably, one might say that this does not represent a true digital twin example, but allow me to make the case. So this is a case. This is an example where we were trying to assess anomaly detection in hydropower plant equipment. Specifically, we were looking at generator guide bearings through vibration monitoring to determine, can we detect the onset of failure, and can we actually detect when these things are going to fail sufficiently in advance so someone can go take some corrective action. Okay, so this is a classic anomaly detection, predictive health management, or predictive condition-based maintenance type of an application. We had data from a single unit. We built a small machine learning model in a simple anomaly detector, time series based prediction. And lo and behold, this shows the model prediction for the vibration. This shows the model prediction error for a different data set from the same unit. And you can see that the error starts to progress early. And there is a point here about 5,000, 55,000 data points in, where the prediction error starts to deviate significantly from sort of the nominal. And that, it turns out, is a trigger point that we can use to say, yes, this is start trending in the wrong direction, stop and go fix it. As it turned out, in this particular facility, they actually caught the anomaly here. And this, and that change turns out to be about 10 days, maybe a little bit over 10 days. So yes, you can do this, right? I mean, this is a simple problem, classic problem. The question is, the model that we've developed here, how good is it? It works in this particular case. It works for this particular unit, but can this be applied to other units? Either other units at the same facility or other units at different facilities. And so this is one where something like a digital twin would help. We don't have one. What we do have is a lot of data from a lot of other facilities that we are working with to acquire, and we can certainly use that to test. But these types of problems have led the Department of Energy to say, we actually need to build digital twin models of hydropower facilities, and there's an ongoing effort that is looking at physics informing or physics-based models, putting that together. But those physics-based models are going to be at the level of the unit. What we also need is physics models for how vibration increases, how wear and tear occurs, and that is again an activity that is just begun over the last 6 months, specifically around bearing and bearing vibration. So those kinds of models and the results of using those models, you can expect to see those over the next year as we move forward. Remember, I said these are all ongoing efforts, so there is no satisfying, here's the conclusion for any of these at this stage. So another example, that kind of gets us, so let me go back here for just a second. Well, that's okay. So the previous example, we have a model prediction, but Carrie had a very nice talk about uncertainty and the need for uncertainty quantification. And the question is, how do you do this uncertainty quantification, particularly when you don't have access to a lot of data or insight into what that uncertainty is? And this is where laboratory scale test beds can come in handy. This is an example where we were trying to determine when the life of, we were trying to determine when a particular material would fail under certain conditions. Turns out that the failure time or the remaining life of this material is a function of the applied stress, but it's also a function of the material, the grain structure, the rolling direction, and we were trying to do this using non-destructive measurements of the underlying condition of this material. And it turns out that the uncertainty is a function of the measurement itself, but also where you make the measurement on this material. So there are a number of sources of uncertainty that you have to account for. Having a test bed like this allows us to explore all of these sources of uncertainty, even if these are not going to show up in an actual field test. By collecting this data, it allows us to build a model for how the state of this material is going to change over time, accounting for all these other factors. And that allows us to do not only remaining life predictions, but also the associated uncertainty or the error bars in those predictions for multiple materials, for multiple specimens. So again, this is sort of starting to get towards this notion of a digital twin. Not quite a digital twin yet, but it's starting to get there, okay? So let's up the complexity just a little bit. Let's start looking at larger systems, right? And this is an example where we're trying to work with a particular subsystem within the spallation neutron source at Oak Ridge National Laboratory. It's called the high voltage converter module. This is one of the power sources that is used to accelerate the beam so you can generate neutrons for various imaging studies. This is a user facility at the lab, but it turns out that the HVCM, or the high voltage converter module, has capacitors. These capacitors, the capacitance can change over time and over a period of years and then fail. And when it fails, let's just say the results are exciting, okay? If you've ever seen a capacitor fail, have you, anybody? No? Yeah, I see a couple of hands up. Yeah, capacitor failures are very exciting. You don't want to be anywhere near them when they do fail. So this shows an example of a failure during transformer saturation. This is a slightly different failure mode. But the question that we were asked is, how do we detect these failures, and can we detect these failures sufficiently in advance so they can prevent these? Data is limited because the system was not instrumented to collect the data. So we want to build these machine learning models for predictive analysis for remaining life calculations. But how do you build these when you don't have the data? And so this is where we started to leverage the combination of models and experimental facilities. So SNS has a test laboratory where they have many of these examples of HVCMs, where we can go in and we can tune them up to a point. They don't want you blowing up those capacitors either, but we can go in and change the capacitance values up to a certain point and generate data. We instrumented that up to collect the data, but we also built models of these systems where we could change the capacitor and use that to generate additional data. So we're now starting to get to the point where you have these models, you have these physical systems, and you're trying to put the two together. Using those data sets, you can build these, we used a Conval STM autoencoder for fault detection. The results were pretty good, as you can see here. But here's another example where the measurement from one of these HVCMs, this shows one of the flux. So there are three measurements, A flux, B flux, and C flux. And it turns out that this is when the fault was recorded in this particular case, but our models were able to predict the fault onset a little bit in advance. Okay, it's still not all that great in terms of how far in advance you can predict, but it is beginning to get to that point of advanced detection of these anomalies. So this is an example where we are combining data from the experimental facilities to build some of these models. We have these physical models that we are also using to understand how the signal should actually change as the capacitance changes, and use those insights to actually build these models. So starting to get towards this notion of a digital twin. I'll skip this. This is actually, there was an at-length presentation on this by my colleague Malachi in the morning session. So I'm going to skip this. But basically, this is another example within the SNS where we are working with these systems. So now we start getting to full-scale digital twin systems. This is an example of a particular facility that we're calling the Facility to Alleviate Salt Technology Risks, or FASTER. FASTER is a flow loop. It is a molten salt flow loop operating at temperatures anywhere between 600 and 800 degrees Celsius. It is intended to support research not only for molten salt reactors, but also for molten salt applications in solar, concentrated solar energy. And what we have is a physical system that, this is in the laboratory. We have a model of the system. This is actually a sketch of the system. We have a full-up thermal hydraulics model for the system that is not shown on this slide. And at the moment, we are beginning to integrate the data that is being collected from this system into the model so you can get real-time changes in state. So it tracks the state of the flow loop itself. What that allows us to do is it allows us to start changing or operating the model, the digital model, in ways that you may not be able to operate a physical model. Molten salt is nasty. Obviously you don't want that on the lab floor. But by using the digital twin, the digital representation, we can do what-if analysis. What happens if I were to close this valve? What happens if this valve was stuck open and the temperature changes and this other thing happens? And so this allows us to start exploring these corner cases to determine not only what happens with the system, but if I have a model that's tracking one or more of these components, how is that going to react? If I have a reinforcement learning algorithm, which we are layering on top of this for control, if I start operating in a completely different mode, how is that going to affect my reinforcement learning algorithm, for example, right? So those are all, I'm about done. So those are ongoing efforts. And I just couldn't get the graphic of the digital twin or the physics model here in time, because that literally got finished up over the last 2 or 3 days. One of the other cool things that we're working on here, and again, this is hot off the press kind of stuff, is the ability to integrate these into AR and VR visualization techniques, allowing you to, allowing an operator to actually go in and start playing around with these systems. So that again is a potential for operator training and so on. So these are potential digital twins. Some of the applications of these digital twins besides T&E that we have been using, we've got a couple of other systems where we've been working with these physical systems and building digital twin models to help detect and compensate for sensor drift. And this is work that's been published in the past. We are also working with a different version of a digital twin for a different system to evaluate supervisory control techniques. The idea here being that you want to keep the system operating in some safety critical region and not allow the system to drift out into a region where it's going to cause all kinds of heartburn. And to do this, we are integrating risk, we are integrating data, and we are integrating predictive analytics or system health into the supervisory control decision making. Ultimately, all of this feeds into cost models and predictive cost models and predictive risk models as well. And again, I'm happy to get into details of any of these if you're interested. So I'll finish up here. Scalable information-driven solutions, including machine learning, are expected to be necessary for managing complex system operation. Like I said, understanding how these systems behave, validating these systems, testing these systems under conditions that we don't have today but anticipate in the future is going to require new ways of performing test and evaluation. And my argument is that a digital twin or some such technology, related technology, may be able to enable robust testing and evaluation. There are a number of examples that we've talked about. There's many other examples that I cannot get into here. Now, one of the things also that I have not mentioned here is the need for standardization. As we talked earlier, digital twins are potentially buzzwords, but they are, as a concept, they are serious enough that a number of entities are beginning discussions and working groups around standardization. And hopefully this is going to lead to some standards and best practices that are put out over the next couple of years. I will stop here, and if there are any questions, I'm happy to try to answer them.
I've got a question about your capacitor failure slide in particular. I feel like I've asked this question probably 4 times today, but it looked so you had an early detection, right? Is it possible to interpret what the model found that triggered that early detection? Looking at your graph there, it didn't look like there was any identifiable features that I could see that at that time that led me to think, oh yeah, something's about to happen. So I'm curious if you can identify what it is that the model is determining early.
At this point, for that model, no.
Okay.
That is something that we are investigating, is how do we get to that issue of interpretability, explainability of the model. Mm-hmm. That is one of the reasons we actually started working on the physics model for capacitor drift and the impact of that on those measurements. So we can at least look at that and try to understand what exactly is going on. Right. But we are not there yet. But that's something that we are working on. Right.
So were you able to look at these time series and be like, you can kind of say, when does it look like it's starting to change? Is that much later than the model is?
For that example, I think that is not so much later than what the model is, and it's sort of picking up what we would have picked up, I think. Okay. There are other examples where the model was picking up much earlier than where we thought we were seeing something. The one slide I skipped about the beam, the accelerator beam, that is an example where looking at the signal, visually it's very difficult to say that is going to fail and that is not. The next pulse is going to be an errant beam, or the next pulse is not going to be an errant beam. Visually, it's very difficult to say that, and the machine learning is locking on to some key characteristics.
Right.
There.
There's something mathematical
There's
happening.
Something mathematical.
Maybe if you did a Fourier transform or something, you'd be able to find it, or I don't know, eyeball it.
It's actually subtler than that.
Yeah.
As it turns out, but that's kind of where we are heading, is trying to make that determination of why is it picking up, because that helps us then in kind of going to the next step of what is it that we need to change.
Right. There's clearly some information in the signal that it's finding, right?
That's right. And so that is an ongoing research effort. But yeah, thank you for that question. Yeah,
kind of related to his question, when I saw the time series in several of your slides, have you looked at using functional data analysis for that type of data? I've seen remaining useful life papers on turbofan engines where they've been much more successful once they started using functional data as compared to other machine learning methods.
Why can you clarify what you mean by functional data analysis?
Well, essentially, when you have a time series, you can break that length into a shape function as well as a sort of run-to-run variation, and then by splitting it, you can actually use the scalar quantities to build machine learning models. So I've also seen examples associated with multiple sensors on a glass encapsulation anodic bonding with semiconductors. And the problem is, when you make that bond, you don't know what percentage of the wafer is still usable until weeks later in the processing. Right. But by looking at all the sensor signals in that anodic bond, you're able to build a machine learning model that allows you to say right now which ones are highly likely to be failures and sort them out now and not waste the processing time.
Right. So, answer to your question is yes. I did not show it in this stack of slides, but in many of the applications that we are looking at, we are working with multiple sensor data, so it's not just a single sensor. And then in some of these applications, we are looking in some applications it's simple enough. You take the time series, you can build a simple enough model that you can do anomaly detection and it works just fine. But in other cases, we have developed two different approaches. One where we are looking at essentially, as you said, here's sort of the baseline, and then here's the run-to-run variation that you can use. The other thing that we've done, that we are actually working on at the moment, is trying to build a model, a machine learning model that is not trying to capture all of the information in the data. What we have is a physics model that captures sort of the basic signatures, or is able to predict the basic signatures, and then we've got machine learning that tries to model the difference. And by combining those two, it turns out we can actually do much better at our predictions and in terms of failure prediction and so on as well. So those are ongoing research activities. I didn't have the slides here because I wasn't sure how much I'd be able to get into in any of those. But yes, certainly that's something that we are looking at.
All right, let's thank all of our speakers one last time. And if you have any further questions, come on up.